In this segment, I want to tell you about the axiom of choice. Now, when you listen to a statement of the axiom of choice, it seems so incredibly obvious that you might wonder, how could this principle be in any way controversial? And yet it is, because it can be used to prove some really, really funky results. So let me tell you what it says. So what it says is that every set of non-empty, non-overlapping sets has a choice set. So here's what that means. So suppose you have a set, and every member of this set is itself a set. So maybe it has one member that's a set AB, another member that's the set consisting only of pi, and 0, 17, 100. So maybe that's your set. So notice that every member set is non-empty, has at least one element, and also that no two member sets overlap. For any two member sets, they have no members in common. So what the axiom of choice says is that any set like this has a choice set, where a choice set is just a set that contains exactly one element from each member set of our original set. So for example, it might contain B from this set, it has to contain pi from that set, and maybe it contains 100 from that member set. So this is a choice set for a given set, and of course there are many others. So what the axiom says is that there always is a choice set. Now, I know what you're thinking. How could this possibly be controversial? How is it even substantial? Let me tell you why. And here I'm going to draw on a famous thought experiment by British philosopher Bertrand Russell. So he asks us to consider two different sets. A set that I'm going to call SH for shoes, and a set that I'm going to call SO for socks. So our set SH consists of pairs of shoes. So you have one pair of shoes there, and you have a different pair of shoes here, and so forth, once for each natural number. And our set SO is something similar, but for socks. So it contains a pair of socks here, and a different pair of socks here, and so forth, again, once for each natural number. And now we're asked to imagine this crucial difference between shoes and socks. We're asked to imagine that whereas if you look at a shoe, you can always tell whether it's a left shoe or a right shoe. That's not so for socks. So left socks and right socks are just the same. They're exactly the same shape. So now imagine that you want to specify a choice set for SH and a choice set for SO. In the case of SH, it's very easy to do. So what you can just say is our choice set consists of every x such that x is in some y, which is itself in SH, and as it might be, x is a right shoe. So the set we've specified here is just the set of every right shoe in one of these pairs. And the crucial thing is that we were able to articulate a criterion which does the picking out of elements that we need for a choice set. But what about our set SO? Well, because there is no difference between left socks and right socks, we cannot use a specification of this kind. So if we really idealize and assume that all these socks are just alike, so they're like photocopies, where if you have a document and produce a perfect photocopy, you have two documents, but two documents which are exactly the same. So if all of our socks are perfect duplicates of one another, then it would be impossible to specify a criterion that would generate a choice set. So now I can tell you why the axiom of choice has real substance. The substance comes because it tells us that a choice set exists even when it's impossible to specify it, even when it's impossible to set forth a criterion, as we did for a set SH, that succeeds in picking out the elements of our choice set. That is what gives proofs that employ the axiom of choice their distinctive flavor. So if you have a construction that relies on the axiom of choice, that is a very good sign that you won't actually be able to tell what the result of your construction is like. Because at some point in your construction, you'll say, well, by the axiom of choice, I know that such and such a set exists. And if someone says, okay, but tell me more about that set, you won't be able to say very much, because if you need the axiom of choice, that means that you cannot find a criterion to specify exactly what the membership of that set is. One might consider the question, should we accept the axiom of choice at all? It clearly has weird consequences. So in this lecture, we're going to see that it can be used to prove that there are non-measurable sets, sets that cannot have a measure. So for example, sets such that if you pick a real number at random and you ask the question, what's the probability that the real number I selected will be a member in this set? The answer is the probability is not defined. Or sets such that if you take an object and you say, this object has a definite volume, but what is the volume of a particular subset of that set? The answer is, again, the volume is not well defined. So the axiom of choice has like all these weird results. The problem is that the axiom of choice is also indispensable for many, many parts of mathematics. If you gave up on the axiom of choice, there would be regions of mathematics where you simply would not be able to prove some of the fundamental theorems. And in fact, we have considered one such field of mathematics, which is the theory of the higher infinite. It turns out that without the axiom of choice, you cannot prove a theorem which you would have thought is extremely fundamental. So a theorem that says that if you have any two sets A and B, then either the size of A is smaller than B, or the size of B is smaller than the size of A, or the sizes are equal. Proving something as straightforward as that requires the axiom of choice. So what most mathematicians and philosophers believe is that we should accept the axiom of choice and learn to live with it.